Okay, so last class we started talking about nearest neighbor methods, which are ways of doing classification and a lot of other things. Okay, the basic idea was that if you've got as a training set a bunch of items, okay, which either have labels, okay, or they have function values, okay, you can build a classifier by identifying, to find a distance measure, identify which examples are most similar to your query input thing, and then take the class labels from the nearest points. Any questions about how that works? Okay, so nearest neighbor classification is a very good thing. It's a very simple thing. This is something I can understand. Okay, it is good because it gives you examples as to why it's making decisions. So, for example, if I were to, build a, what might I want to do for let's say I was going to try to classify a movie, okay, what genre it was. That was one argument we gave. If I took a look at a movie and it came back and told me it was a comedy and I was astonished, I would be able to ask which were the movies that you said I was closest to that made that decision. And I would learn something. If that was a clearly ridiculous thing, I would learn something about why those were the nearest things. So nearest neighbor classification is a good idea, and this we have talked about before. And I'm going to talk today about more other ideas related to that. So we're going to keep going on that. So I gave the introduction last class. One thing that I didn't mention that is a good idea also is you can use nearest neighbor for regression things. What was regression? Remember, let's say that we had a bunch of training examples, okay? You had, n training examples. You had each of which had m features. And let's say there was a target thing you wanted to predict. Let's say you wanted to predict their income. You had data about people, how tall they were, how heavy they were, how many years of college they had, things like this. You could also, if I gave you a query value, one way that you could, if I wanted to I have a new input record and I'd like to try to predict what would be the income for this person. Notice that I can do that by a nearest neighbor method as well. If I took a look at who of my examples were the closest ones, okay, in terms of most similar to my input record, then if I were to average or take the median of the incomes I saw there, that becomes a reasonable predictor for, in some sense, I think of classification problems as you have a small set of possible labels. I think of regression values as you're trying to predict a function. Okay? These same ideas can be used for regression. Any questions? We usually talk about it for classification, but this is sometimes a very good idea. Any questions? Okay, fine. So, nearest neighbor classifiers, the strictest thing is if I have n training points, go through and find which is the closest point to my query, and then report the label of that. There is an obvious generalization of that to the k nearest neighbors classifier, where instead of finding the single closest point, you find the k closest points and vote among the labels of that. What would be the advantage of using a larger k? Okay, k equals 1 is the default nearest neighbor classifier. What would be the advantage of having a larger value of k? Accuracy? I would say accurate. Okay, I mean, we want to be more accurate, but more specifically, accuracy. I don't know for sure if that's. I mean, I'd like that to be, but it's not obvious why that should be. What I would like to think is I would improve the robustness. I have more evidence to make my decision if I am basing my label on several nearest points rather than one nearest point. Does everybody see that? And so, in general, using more than one nearest neighbor is a good idea. So here is, I think, an instructive example. This is sort of, remember, we had points in height, weight space, and we were trying to identify who was a male or a female, I guess, is what's presumably happening here, right? And it looks like the females presumably are lower in height weight space, the men are generally in higher weight space. Now notice that when we have k equals 1, or in fact any k, what the nearest neighbor classifier is really doing is carving space up into regions such that we can define a region where all points that have the same nearest neighbor are in part of the same region. Okay? And weird things happen when k equals 1. For example, look at this point over here. Okay, what is this thing doing? This is presumably a woman who is unusually heavy and tall, right? Now, because she's in a strange part of the space where there's relatively other few points around her, she is the closest point of all the inputs for everything in this red region. Does everybody kind of see that? There's a blue point out here, there's a blue point out here, so you have this long skinny region where she happens to be would be the nearest point of. Does everybody see that? And the net result is that for anybody who weighed 180 kilograms, we would define that they are a woman based on that one point only. Does everybody see that? And, you know, it's probably a little more sensible in the denser parts of the space. Okay, the regions around, again, we look at this thing, there are blue points here. Again, I don't know quite how well you can see it from where you are. There are blue points out there, but the blue points here dominate very small regions because there's a lot of red points around them. Does everybody kind of see it? The reason why this is really bad is that you've got a red point with very few other, a outlier with very few points around it. Okay? So what is good about nearest neighbor is that it generates a reasonably sensible classifier generally. It is nonlinear. Notice this decision boundary is jumping all around. The bad thing is at certain points in the space it is making its decision based on, at every point it's only making it based on one point. And that leads to problems. If you make k larger, what ends up happening is, this point, if k is equal to 3, suddenly this region goes away. Because no matter where you look around this thing, any point where you look at the 3 closest points, 2 of them are going to be male and 1 of them is going to be this female, right? So her region of dominance has gone away, okay? There still are a few weird artifacts. This point seems to be isolated enough and near enough to another woman that this one kind of stands out. Okay? But if we make k larger and larger, at some point it generates a relatively smooth boundary. Okay? And the exceptions have kind of gone away. Any questions about that? So what is the advantage of a larger k? Larger k is to find better supported region boundaries. Okay? In general, the classification is probably more accurate, unless you really want to tune into the weirdnesses of this thing. Any questions? Yeah.
Would there be a disadvantage if we take k to be a very high value?
So what would it happen if k was a very, very high value? Suppose we took k equals n minus 1. What would happen there? Okay? Then basically almost the entire plane, if let's say there were more men than women in the training example, everybody would be a man. Does everybody see that? Let's say k was equal to n minus 1, and you had a couple more men in the training set than women. One result of that would be there would never be any place in the world, pretty much, presumably, where it'd be possible to be a woman. Okay? So at some point you would lose some discriminative ability if you jack it up too high. How high should it be? The higher you jack it up, the simpler the boundary gets. My instinct, without giving you a proof, would probably be if you jack it up high enough, maybe it gets simple enough it kind of becomes like a line, and maybe it becomes more like just a linear separator, right? And if you jack it up even higher, it becomes presumably just always picks the majority element. Okay? So there's a little bit of an art here in setting the right value of k. You want it to be able to adapt to local things. I have no doubt that this is better than if k equals 10, I have no doubt that this is better than the linear classifier in that, there does seem to be this region that is probably more likely to be women. The fact that there is this bend, to me, I suspect that's a real thing. Okay? Any questions about that? Okay? So, typically, how would you set the value of k? Let's try that. How might you set what the right value of k is on a particular one of these things? Okay, you want to build the nearest neighbor classifier for a given k. How would you set what might be the right value of k? Right. So if you took your training examples, hold some out as evaluation things, then what you might want to say is, if I set k equal to 1, what's the accuracy on my holdout thing? 2, 3, 4. The hope would be you would get presumably some kind of a dip, okay, whereas k got larger, the error would get lower to some point, and then it would presumably stop getting lower or maybe reverse. Okay? So that would be the logical way to set what this thing is. Any questions? Okay, good. Now, there's a philosophical idea behind nearest neighbor classifiers that I like, that is, I think about it, is that what nearest neighbors are doing is that they work by selecting, in some sense, analogies. I am making a decision that this is a woman because this person is like these women. That's kind of what it would have been, right? And, I don't think in computer science or mathematics that's not the usual way we think, but a lot of the world, intellectual world, thinks in terms of analogies. Okay, and I think it's a useful thing to think about. In law, how is it that people, lawyers try to prove which side should win or not? At least in the American legal system, and I suspect probably in a lot of the other ones, there is an extensive record of past cases. And you will go to the judge and you will say, look, in this case, you had this student who was beaten by their advisor, and and the advisor was, and then you would say, well, look, here are 5 other cases where here you had one of a student beaten by an advisor, here you have a teacher beaten by the principal, and in all cases the leader got sent to jail, so you should send the advisor to jail. That kind of thing. So thinking about legal precedents is like analogies. In medicine, a lot of the decision making that doctors go on is, I claim, based on analogies. That, the doctor says, they see a patient walk in, they look at this guy and they're thinking back, okay, I saw someone back like this, okay, I gave him this drug, he died 3 days later, okay, I probably shouldn't give him that drug now, right? Said I gave somebody else this drug and they survived, okay? So again, I think that there is this notion of analogies. And a lot of models are based on analogies. For example, when you buy a house, when people buy and sell houses in this country, how do you set the price that you should be charging for a house? Usually they will say, oh, give me comps. What does comps mean? Comp is a comparable house, okay? So you would say, look, this is a 3-bedroom house. It's got a pool, okay, and it's got nice trees. In this neighborhood, there are 5 3-bedroom houses. 2 of them have pools. The prices these had were like this, and they try to reason out a price that way. And this is the same kind of a philosophy as a nearest neighbor kind of a search, okay? And I think that looking for analogies just as a philosophical thing is a great way to reason about a lot of problems that a lot of people don't really think about, I like to think about analogies. When I think about, if a student is coming to me, should I take this student on for graduate studies? I think, what does this student look like compared to previous students I've seen? Students that looked like this, they all became duds, okay? So, So, I should be suspicious of this one. Okay? Any questions about it? Okay? And I think that's important. Okay, so let's just think about this nearest neighbor analogy-like idea and quickly go through some of the challenge problems, the quant shop problems. How would we use a nearest neighbor idea to try to find who would be Miss Universe? What would be the idea that you would do something like that? Okay, yeah?
Yeah, just who won in the past, what characteristics.
Well, what you did is you had records of the contestants here. You had records of contestants that won or didn't win. You say, who is this contestant most like? If they're like a winner, then that's a good sign. And if they're like a loser, that's a bad sign, right? How would we predict movie gross?
How much is similar movies grow?
Yeah, so you need, in some sense, if you have a way of gauging how one movie is similar to another, some distance function between movies, in feature space, based on budget and number of theaters that it's opening in, and the rating and the genre and stuff like that. Now you can make some kind of a sense. You can use it sort of as a regression thing. The 5 closest movies to this grossed between 10 million and 35 million. And that seems like a logical range, so maybe I'll pick the middle of it or something like that. Okay? Baby weight, how would you find, again, the same kind of an idea, right? You look at the vital statistics on the mother and for this one, and you look at what other moms were closest and what came out of them. That's basically the question. Okay? Any questions? Art auction price, this is very much an analogy thing, right? You see a painting coming up, okay, this is impressive, okay? Okay. If a painting came up for auction, what are the other paintings that were most similar to this, and how much did they sell for? That would be kind of a good way to make such a prediction. Any questions? I think for almost all of these things, there is, I claim, a logical nearest neighbor model that can be defined. Well, future gold or oil price, how would you try to figure it out? I think that an analogy with times is probably, if you take a look at, given this situation that we have now, what? Gold prices went up. They happen to have gone down over the last very recently, but no. I mean, the kind of thing what you would want to look at is how do the times, like for example, try to predict what gold's going to do. What if we have a record of what the economic situation is at this point? Where were there other points in history that had similar economic situations, and what happened to gold then? That would be the analogy kind of a thing, and I suspect that that's probably a reasonable way to do it. Yeah.
Are there situations where drawing an analogy is a bad thing?
Can drawing an analogy be a bad thing? The answer is yes. You draw a bad analogy.
It's not a bad analogy.
Yeah.
But generally, is for example,
is there a systematic argument that drawing analogies are bad? What I would probably say is if your data has some kind of a bias that it was drawn in, probably analogies are kind of bad. Okay? So if you think, it's off the top of my head that, one, let's say, bad idea of this is sort of a prejudice idea. Another way to think about analogies is a question of, if you train on some kind of a model where you have a bad impression of, lots of people, and you apply it into a different domain, it's probably a bad, you get wrong ideas. So I have no doubt that, if you're a policeman, I have no doubt that, after dealing with, miserable, crooked people, your entire life, you develop a different sense. When you look at people, you're more likely to probably classify someone as a miserable, crooked person because that's the examples that you have, right? But in general, I think, again, if you have good representative examples, I think analogies are good ways of thinking. Any questions? Okay. There is an algorithmic issue in finding nearest neighbors that is interesting to talk about, okay? So what is the running time? If I want to do a nearest neighbor classifier, if I have endpoints each of which has, m features. I give you a new query point which has m features. How much time does it take to find the nearest neighbor? Okay. It should be order nm, right? Because it would seem like the default thing to do is that it would be, in linear time, to compute the distance between 2 points is proportional to the number of features. Do that times the number of points. This is something that would be n times the number of the features. Okay? So one interesting thing about nearest neighbor classifiers is, as you originally think about it, what's the training time to build a nearest neighbor classifier? Okay, it's kind of an interesting thing. You say n squared m. I would arguably say nothing. What are your points? Here's your points, okay? Boom, there's your nearest neighbor classifier. How much time does it take to run the classifier on a new instance? Then that would be order n times d, right? But to train it, well, there's no training on some sense, right? If you fix what your k is, it's, that's that, right? So the interesting thing is that training speeds are fast, but for large training sets, actually doing the queries of nearest neighbor classifiers are expensive, okay? Any questions about that? And so we would like to, if possible, build some kind of a data structure that will let us find nearest neighbors more quickly, okay? Or maybe even approximate nearest neighbors more quickly. Because if you've got, a million houses or a million training examples, any query is going to take a lot of time. Any questions? Yeah. No, I want to say that basically when you say what is the training time to build a nearest neighbor classifier?
But you just specified how many groups you want.
I specify k. Okay, is that training? Quite often that's what should k be? 15. K is 15. Okay.
But you need
K. No, I don't need to find central. I don't need to do anything. Okay. If let's say I'm just building a simple nearest neighbor one, I'm going to report the class of the nearest neighboring point. All I have is an array of n by m array containing the points. What else do I have to do to prepare to be in the classification business? Nothing. Okay? To actually classify something, I've got to look at all my training examples, right? Is it the number of training examples, the preparation time? I say that if think about it, the training time is till you're ready to go into business to say, I can now answer queries, right? So I'm going to separate, there's a training time when somebody gives you data, and then you want to know how long from now can you advertise that you have your classifier done. Okay? You can advertise immediately with nearest neighbor. With linear regression, you've got to actually, you've got to do some algebra, you've got to go gradient descent search, you've got to do something, right? Any questions? Yeah.
So if you have m features like this, and then what should ideally be on k? How should k and m?
Well, as I would say, how would we set k? We discussed that a little bit. We said that, k is the number of points that you would like. In general, you might want to say, don't give me the label of my nearest point, but maybe the most frequent of the 3 nearest points. Okay? That would be k equals 3. And again, typically the way you would set k is you would try different values you would have a test set. You would train, if actually you want to figure out what the optimal k is, then yes, there is some fitting. Okay? And that could arguably be called training. You would hold out some examples. Okay? Run this with different values of k and see which it does best on those examples. Yeah.
There are predefined methods, right, to find this value of k within the algo function, within sum squares, and how.
Well, okay. So again, it should be clear that, and we'll talk a little bit about this elbow functions more related to clustering and stuff. But you're right. If we tried a different value of k, we set out some examples for evaluation. There's going to be an accuracy level for each value of k, right? And generally speaking, we would want the k that maximizes the accuracy value on that thing. and to figure out what that k is, would be training. Okay? So if you want to find the k that does best on this, that's training. It takes time. If you want to rule by fiat and say k equals 15, there's no training. Yeah.
Accuracy meaning just like what minimizes the amount of distance between the points?
No, so it's kind of like, if we have a bunch of training examples and we have a bunch of testing examples, and this I know is man, woman, woman, man, okay, I could try to classify these on these examples first for k equals 1, right? And if I got woman, 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 I'd say, oh, that got 50% right. And if I now try k equals 3, maybe if I took the majority class, now maybe I got 75% of them right. And if I did k equals 5, I got all of them right, maybe that's where I would stop, right?
K equals 3 meaning you get like 2 women's and a man for like a man, or sorry, for a woman.
So by k equals, by k, what it means is that I pick not, for k equals 3, I pick for any point that I'm classifying, find the 3 closest points,
Right.
and then vote among the labels.
Right. So if there's a majority of those.
If the majority of them are women, the point's declared a woman, otherwise it's declared a man. Okay? Any questions about that?
Is there any data structure which performs exceptionally well?
Okay, so let's now think about data structures. So we kind of agree that in general, the problem with nearest neighbor classifiers are that it's expensive to find the nearest neighbor. Are there data structures now that we can take these points and build something on top of the points to make it better to do those kind of classification? There are several interesting data structures that I want to review quickly. Okay, at least some of them. One of them that many of you are how many people have ever heard of what a Voronoi diagram is? Okay, a Voronoi diagram is a decomposition of, if you have a set of points and you decompose space into regions such that every region is defined by the set of points that are closest to it. Okay? So let's say that we were building a nearest neighbor classifier and we only had 2 points. What would be the, this I want to get rid of. How do I do that? Let's hide it. Okay? Suppose we had 2 points. This is XY space. What would be the way that space would be decomposed based on who's nearest to this? Which are the points that are nearest to this? What's the magic word? Circle? No. The points that are nearest? No. What are the points that are nearer to this than nearer to that? The boundary. What's the boundary between them? Perpendicular bisector. Remember that? If we found the perpendicular bisector between these things, that would divide the point into zones such that if this was a man and this was a woman, every point below the line should be called a woman, and every point would be above it would be a man. Does everybody agree with that? And if I add a third point here, let's say now I add a third point, okay, then what should the regions be? Well, between these two guys, it's probably the perpendicular bisector. Between these guys, it's probably the perpendicular bisector. You get a cell that looks something like this. Does everybody kind of believe that? And in general, if you do this with endpoints, you get something that looks like this. Okay, and this is called a Voronoi diagram. And what's good about a Voronoi diagram, now the question of who your nearest neighbor is reduces to which cell are you in. Does everybody kind of get that? If I knew what the name of the cell that I was in, that would be telling me what my nearest neighbor is. Yeah?
But then you need to, never mind. I lost that.
Okay. So one idea that works in small numbers of dimensions, best 2, but sometimes perhaps a little bit more, is to decompose space into build a Voronoi diagram. It turns out you can do that relatively efficiently. There are algorithms that will let you find in 2 dimensions what cell are you in something like log n time. Okay, sort of like a binary searchy kind of thing. Okay, and so that would be a great, in 2 dimensions, that's a great way to do this, right? Now the trouble is Voronoi diagrams get complicated in higher numbers of dimensions, okay? And they get to be very large, they get to be harder to search, okay? So in general, for small numbers of dimensions, maybe you could use a very small number of dimensions, you could build a dimension, you could build a Voronoi diagram. Another idea that is useful in a higher but still not infinite number of dimensions is something called a KD tree, which basically is a binary tree that divides space in pieces. So if we look at this thing, here we have a bunch of points. I originally have as the root one line that goes through a kind of a median-like point that divides the points into those that are on the left and those that are on the right. Does everybody see that? And then among the left points, I now switch dimensions. And I say, where is the dimension of all the points on this side? Where would the median be? It's probably about here. And now that's going to be define the children of this thing. Okay? So you can kind of picture that we've got a hierarchy of cuts. This thing would be now a cut here like this. This thing would define, this region and this region. Does everybody kind of get that idea? And over here, if, let's say I did a cut here and a cut here. This is now going to be this. This is going to be the top part and the bottom part. Do people see what I'm doing here? I'm recursively dividing up spaces by dimension. I'm alternating dimensions in some sense. And I am building a tree. So if I want to figure out which box contains this point, how would I do it? Am I to the left of this main cut or not? It is to the left of this main cut. So that gets me on this side. Am I above or below this cut? The answer is I'm below, so therefore I'm in there. Does everybody kind of see that idea? So you can try to build a tree of splits, okay? And if so, if you follow for a particular point where it should go, you will presumably end up in a box that's ideally the box you want or close to the box you want. Okay? Yeah?
The KD trees are for representing Voronoi diagrams?
No, this is an alternate idea. This is for representing points. We're not going to build these actual bisectors. We're going to build axis-oriented cuts that are easy to test, okay? And build basically a rooted tree to help guide us to who our nearest neighbor is, okay? Why? We want to decompose the whole space into boxes, but because we're doing each decomposition is by a slashed cut that goes through it, to decide whether I'm on the left or the right or the up or the down of the cut involves basically comparing one dimension against my query point. Is the x value greater than 3? If so, you go to the left. If not, you go to the right. Okay? Any questions about this? So this is done by you take the training points and you're building what you want to do. Okay, here's what you would like to do. You would like to take the space and carve it into regions such that each region, let's say, has a point in it, okay, or is defined by boundaries of the points. There's a couple of different variants of this you can do. But you'd like to have you'd like to make it quick to identify what is the region that contains a particular point, right? That's kind of what we would like to be able to do, right? So what our tree here is we're going to define our tree by a sequence of recursive operations that originally there is a space of the entire points. We are going to pick a median in some dimension and cut a slash through it. That's going to define the root. This slash is going to say points on the left of the slash line go to my left subtree. Points on the right of my slash line go to my right subtree. Then within the left piece, which is this, my next slash line is going to go according to a different dimension, y. Does everybody see that? And then am I above the y or am I below the y? That, again, partitions the space into two pieces. If I do this based on medians, okay, median points somehow, after log-ish height, I should have every cell basically, empty, okay, or has 1 point in it, okay? And so therefore I can traipse down this hierarchy and find a box, okay, that contains a particular point, okay? Any questions? Yeah. Yeah. Okay, so now the question is, again, my goal is to find the nearest neighbor, the nearest one of these training points, right? Now, perhaps what we would say is that the nearest neighbor for any point, ideally, would be one of the points on the boundary of the box. Does everybody agree that at the end of this I've got a bunch of boxes, the whole plane is, and these boxes are defined by contact points, right? So one reasonable thing to do might be, if I find that, once I have found that my query point is in a box, find the points that define the boundary of that box and pick the closest of those. Okay? That would seem like a reasonable guess at who the nearest point is. It's not perfect. Can we see a place where the nearest point, so for example, suppose I looked right in here. Can you guys see where my arrow is or not really? Okay? If I went right in here, okay, where was I don't see it. Okay, so that's why, okay. If I went over here, the nearest neighbor to this is this thing. Does everybody agree? The nearest boundary of it would be one of those two. That would be it, right? So as stated, this doesn't quite get us the nearest point, okay? It gets us good candidates for the near point, right? And with searching other boxes that are nearby, can, at some cost, provably find the nearest point, okay? Any questions about that?
Is it the same as the previous diagram?
No, this diagram, if you look at it, has funny, slanty, perpendicularly bisecty things, and this thing does not. This thing is built of axis-oriented lines that, that build a tree decomposing space. Okay?
Ultimately, we're looking for the neighbors in each of these things, right?
You'd like to know for every box who are the candidate nearest neighbors.
Yeah.
So once I know the idea is that once I know what box I'm in, there should be very few candidates for my nearest neighbor now. Does everybody agree? If I'm in this cell, can this guy, any one of these points, be my nearest neighbor? No. Okay? It should be clear that, the nearest neighbors, the ones that really bound my cell, are good candidates for the nearest neighbor. There's probably some other ones in somewhat nearby cells that are also possibilities. Okay? So there's lots of different variations of algorithms based on this idea, depending upon whether you want to get an exact nearest neighbor or whether you're willing to be faster and get an approximate nearest neighbor. Does everybody kind of get that idea? And for a lot of things, maybe you're content with the approximate nearest neighbor, right? Okay, if I want to do, I find the 7 approximate nearest neighbors, I do a majority of those. Is that probably going to be pretty good? Maybe it's pretty good. And maybe it's worth, instead of taking order 1 million time, if I took order log million time or 10 steps to do that, right? Okay, any questions about that? Okay, so this is one other class of data structures. Now the trouble is that as the dimensions, when you get to beyond 2 dimensions, Voronoi diagrams start to get iffy. Okay, maybe 3 dimensions, maybe. KD trees are good probably up to, I would say, about, I've used them for up to like 20 dimensions or so, and they do something, okay? As you get high enough number of dimensions, what these boxes look like get kind of weird looking in high dimensions. And the nearest neighbors can be many, many boxes away from where you actually are as the dimensions get larger, okay? So for very high numbers of dimensions, it ultimately reduces to linear search. Any questions? There is one other idea that is a new popular idea that's actually kind of clever, called locality sensitive hashing. That is another approach for finding near neighbors. It's not going to find the absolute closest neighbor, but it is a fast way to take a bunch of points, a large number of points, and make it likely to find the point that's pretty close by, or perhaps the nearest neighbor, okay? And what is hashing? You guys should know a little bit about what hashing is. Hashing is this idea that you take your object and you convert it to an integer, right? And the reason we used it originally was for building hash tables, and when you were building a hash table, you wanted two items that were very similar to each other to hash to different keys, right? If you had, if you had Steven Skiena and you had Sammy Skiena, you'd like them to both end up in different buckets if you were building a normal hash function. Now, locality-sensitive hashing is trying to do the different thing. It's trying to assign points to buckets in such a way that if 2 points are close to each other, they are more likely to be in the same bucket. Okay? That's what we would like to be able to do. So this is different than our traditional hash function. Any questions about that? Let me show you a little bit how it works. Again, the goal would be we would like to take either points or vectors. I'm actually going to talk more about vectors now. But basically, and such that the hash codes of two vectors are going to be equal to each other. It's likely that the hash codes are equal to each other if the 2 points are near each other. The closer they are, the more likely they are to stay in the same bucket. Okay? Any questions? How can we build such a thing? And this is actually an interesting idea. Let's say that we were dealing with vectors, so we had points on a sphere, and we wanted to quickly try to be able to hash the points so that points that were near each other on the sphere would be in the same bucket. Okay? Now, in 2 dimensions, maybe you would divide the angle ranges up or something like that, and say, in this angle range from here to here, those are in the same bucket. But think in general, you've got a large number, a sphere and a high number of dimensions. You've got points scattered on the sphere. How can we give each point a label, a hash code, such that nearby points are likely to get the same hash code? One idea is to pick a random plane that cuts through the origin. Okay? What do I know? That a plane that cuts through the origin has a formula to it, right? And if it was a line, it would just be basically described by the slope. Is that right? In 2 dimensions, it's described kind of by 2 parameters. Does everybody see that? So what if I picked a random plane, okay, and then if it went through the origin, my claim is that it partitions the points into 2 sets. Those that are above the plane and those that are below the plane. Does everybody see that? So what I could do is say, any point that is above the first, let's say I pick this one random plane, my first plane. Any point that is above it, its hash code is going to start with 0. And if any point that's below it, its hash code will start with 1. Does everybody see that? Now let me pick a second random hash plane. And now again ask, all the points that are above it get a value of 0. All the points that are below it get a value of 1. Does everybody see that? And if I did this for k times, I'm going to have a pattern of k bits such that for every point is going to get represented by a string of k bits. Does everybody agree? And is it clear that if 2 points are relatively close to each other, they are likely to end up with the same hash code, right? If we had these 2 points here, okay, that were very, very close to each other, how could they, the only way they could get to have different hash codes? The random plane cut right through them. Does everybody see that? Okay, and the closer they are, the harder that is to happen. Okay? Any questions about this scheme? Yeah.
Can you prove anything about how big the slices are going to be, or like how likely, like could you end up with one really big slice and then like a bunch of really small slices or anything like that? Or
Well, there is a theory about how accurate, how well this should work. Okay, help you choose these kind of, if you think about it, there's a couple of different ways you could do this. One is, what parameters do you have at your disposal? You have at your disposal, first of all, how many bits you use for this thing, right? You also have at your disposal how many hash codes you make for each point. Maybe for each point you'll make multiple different hash codes, right? And then you and I are neighbors if we collide on any of them. Does that kind of make sense? So maybe if I constructed 3 hash codes for each points, maybe one of them, the line did cut through those 2 very close points, right? But odds are in the other 2 it didn't, okay? And that these points might very well get the same hash code in at least one or many of them, right? So the bottom line is there is a theory for how you would kind of do this thing. You wouldn't want your, to accept a split if it didn't split through a lot of points, right? It'd be bad if, let's say you had, with this scheme, if all my points happened to live here, it would be bad to be picking these as my random planes, right? So, so you might want to, pick a plane, see how well it works, and if it's bad, discard it. Yeah.
do you put the points on a sphere? Is that
Well, how do you put points on a sphere? Remember, we had this idea that you could treat points as vectors, right? So if you think about any point, if you have a point in space, there is a point out here, what could we do? Well, we could draw a line through that to the origin, right? That gives you a direction. And now if we divide by the length of this, that gives us a point on a sphere. Is that right?
okay?
So this is that, a natural thing to do, right? Yeah. Can you put more than 3 dimensions on a sphere? Yeah, you put it on a 4-dimensional, on a sphere, or a 5-dimensional sphere. Okay, so a sphere, what's the formula for a 5-dimensional sphere look like? It's going to look something like, if I am correct, x squared plus y squared plus z squared plus, now we run out of letters, but let's try a squared plus b squared is equal to 1. Does everybody agree that that's the formula for a 5-dimensional sphere? Okay. So the answer is there's spheres in as many dimensions as you want to live in. Okay. And you can do the same kind of thing for that. Yeah.
Once you have your key bits of strings, how do I ever test for something, say something like accuracy? I mean, how accurate are my eventual neighbors or something like that?
How would you test how accurate this is? Well, one possibility, of course, is you do it with a certain number of points, and you hold out some points, and you ask yourself, gee, for certain points, maybe you could compute, what the, empirically, if you wanted to do that, right? You could say, okay, here I had 1,000,000 points. For 10 of them, I actually computed the brute force neighbors and looked for them. I found this way, and the nearest neighbors that reported otherwise were pretty close. Okay.
There's only an imperative. There's no.
Well, there is a theory. This is definitely the product of a theory. Okay. Just like with any of these hash functions, there's a whole theory behind hash. There's a whole theory behind locality-sensitive hashing. So there are guarantees that you could get as to how you would engineer such a thing. Okay? But, yeah.
I don't get how will we have multiple hash codes for a single point.
So what would happen, let's think what we're trying to do. If I want to try to find my nearest neighbor, what might I do? Okay? Perhaps I could build a hash, a hash table. Let's say I have n points, right? One possibility is I'm going to build a hash table with, let's say, let's say I'm going to build it with n buckets. Okay? So n is going to be equal to 2 to the k for some value of k, right? Suppose I have my n points and I just compute a k-bit hash value for it and store it in a hash table. You know, yes, similar points should get to the same bucket, but it's quite possible for them to miss. Does everybody see that in this case, this point and this point were very close, but they would have ended up in a different hash bucket, right? What if I now go and do this again with a different set of random, planes? Now I get a second crack for points to collide, right? And if I do this, let's say, a couple of different times, let's say I did this 5 times, okay? Any point, if I hash my particular point, my query point, according to each of these 5 set of lines, there's going to be some other residence in the bucket. Is that clear? Yes. How would I find my nearest neighbor? I would go through all the residents of the same bucket and compute the real distance between us, right? And the hope would be that the smallest of these would be the nearest neighbor, the actual nearest neighbor, or a good candidate for that. Any questions? You see, if I do it a second time, I'm more likely, I get another chance for my nearest neighbor to be in my bucket, right? And so there's a chance I will see that guy, okay? It'll be twice as expensive to do, but I increase my odds I'm going to get the winner, okay? And this then becomes a balancing act. How much time are you willing to spend versus how much do you want the winner?
Do we always use a 0 and a 1 bucket in this? Like 2 buckets, either 0 or 1, or we can have multiple buckets also?
Well, I think that I like this scheme of using it as we're building a binary string, right? And any number you represent in a computer is binary, right, ultimately. So this doesn't seem that, this isn't really that weird. It's just like a number, right? Okay, but we're building it up in a way that 2 numbers will match if they agree in all k planes, right? Any questions about that? Okay? So this is a good thing. And note that you could use in general, what sometimes you could do is use these hash functions almost as features for what the thing is, right? So there are various techniques for building features from objects based on locality sensitive hashing. You have this huge dimensional space perhaps. This gives you a way to find a smaller number of dimensions of representation for the thing. Okay, which in some binaries. Anyway, this is an interesting idea. Yeah.
Like when we draw the first plane, suppose.
Yeah.
Then I think it will create the maximum distance because the first 0, 1 will be the most significant thing in the whole string, right?
Yeah.
We go for like next.
Yeah.
Then they will create smaller gaps.
Okay.
I think the first one will be the biggest gap, then it will be smaller next thing. So it comes from the bias.
Okay, no. So what's true is that if we interpret these as numbers now, integers now, okay, is it clear that the first plane we used would have the most impact on it as an integer? The answer is yes. But we're only using it as an integer for testing equality, right? You don't get any points for being big. You get points for having somebody else in your bucket, right? So the hash codes are going to be used as buckets so that 2 points that had the same hash code are candidates for being nearest neighbors of each other, right? We don't care if it's in a big bucket or a little bucket, right?
What I want to say is that if suppose for the first plane, 2 points are quite near, they got separated. So I mean that they will have a big difference.
Once they are separated in any bit, then they will not be equal hash codes. Does everybody see that? So if I'm only going to consider as possible nearest neighbors ones with the same hash code as me, it doesn't matter if we differed in the first bit or the least significant bit. We're different, right? We don't hash to the same place. Okay? Any questions about that? Yeah?
So if the hash codes are not matching, do we consider those which have the maximum bits same?
No, so under this scheme, basically, since maximum bit is no different than the minimum bit,
No, I'm talking about number of bits being parity. So number of ones if you add them. If you add the hash codes for two.
okay, so what you're saying is, if I wanted, one notion of closest point might be the one that has the smallest Hamming distance between me and this space. And maybe you're right, but in order to compute that, I've got to AND me with every one of these hash codes. This is now order n again. This is what I was trying to avoid. Does everybody see? I don't want to look at all the input points. What I want to do is to build these hash tables. And then when my new evaluation thing is, who's my nearest neighbor? Well, hash me. I go into a bucket. These are my possible nearest neighbors. Okay?
So won't that put a restriction on us that if there are too many classifiers, if there are too many planes, then it's very much possible that we won't get any nearest neighbors?
So what's clear is that the more planes we have, the fewer points per bucket. Okay? If we are unlucky, our bucket might be empty, right? Okay, so we may not want to go all the way down to where buckets are expected to be empty, right? Or we may want to make a couple of copies of this. And so if I happen to be hashed to an empty bucket here, unless I'm hashed to an empty bucket in all of these, I will have somebody as a candidate neighbor, right? And so this is where the art of designing these things is. You know, I want to maximize the chance that I will get a neighbor. I want that neighbor to be generally close to me. I don't want to spend much time doing it. This is now an engineering issue. Okay? Any questions? But the interesting thing is this doesn't care anything about how many dimensions it is. Right? It's happy to slash, I don't care about how many dimensions it is, really, to some extent. Okay? And I don't really care about how many points there are, because, you know, basically, you know, the size of my hash pattern is probably going to be log the number of points, or something like that is a logical rough size for it. So this should be fast. It should not worry about dimensions, and it's generally a good thing. Yes?
So this is a hash function in which we actually want collisions, right? Like
This is a hash function where we want collisions, exactly right. We want the right collisions. We want collisions that are nearby points on the sphere. It's very easy to design a hash function that will get a lot of collisions, just set everything to be 0, right? And then everybody's tossed in the same bucket. But we would like to be a little more refined than that. Any questions?
So,
Yeah.
in this case, I believe that then we should have a number of optimal planes that we can have. I mean, too many planes also should be bad.
It should be clear that too many planes are just are bad, because then almost nobody, you know, is going to be in that. It's unlikely anybody is going to stay in that bucket with me. Too few planes is bad because you have a lot of points to search, right? Sort of a Goldilocks thing, where is it just not too hot, not too cold, just right. And in principle, something that is log n-ish is probably about the right place. Because if it's log n, then in principle, every bucket should have about 1 point, right? And if it's, you know, if it's one less bit, it would double the number of points, right? So, you know, you can, you know, that gives you a ballpark area to be living. Okay? Any questions? Okay? Fair enough. Okay? Any questions? Okay? Fair enough. Okay, so what I wanted to talk about now is, so we've been talking about nearest neighbor things and points, okay? We've had this idea that, again, how nearest neighbor classifiers work on point data, which is generally, a reasonable thing. What I'd like to show you is that there is a connection between points in space data and networks that we will exploit, because there's certain, many data sets clearly have natural interpretations as networks. This much, I guess, is not news to anybody, right? If you want to model a World Wide Web, you could model it by a network where the vertices are pages and edges are hyperlinks, if I link to you, okay? If you want to model people's interactions, you have a social network. The vertices are people, the edges are who you're friends with. Is everybody clear about that? There's a lot of things in the world where data sets which are naturally represented by networks. Often, if you work for a company, you have product-customer networks. Some vertices are products that you sell, some vertices are customers. There's an edge if this customer I bought product J, okay? And all kinds of things can be modeled by networks. That much should be clear. What I wanted to show you is that there's thinking about point sets often can be reduced to thinking about graphs, and thinking about graphs can often be thought about working with point sets. There's sort of a little bit of a duality thing here. How can you interpret, what would be a natural way to turn a set of points into a graph? Let's think about it. If I have a set of points here, is there a way I can naturally make a graph out of it? Well, one possibility is I make a complete graph where I said every point is connected to what other point. That'd be a complete weighted graph. What would be the weight, the logical weight to assign an edge? The distance between them, right? And that's what I'm kind of doing here. Here I have points, here I have a distance matrix, right? How could I turn a point set into a sparse graph? Join points that are close enough, or maybe only keep my 3 nearest neighbors or something like that. Does everybody kind of get that idea? So there are things that are good to do on graphs. It is often a natural thing to take a set of points in space and build a graph on them. Does everybody kind of see that? Is there any way we can go from taking a graph to defining points in space? Okay, is there anything we've done in here that, given a network, could we represent each vertex by a point in space, okay, in some natural way that encodes the structure of the graph?
At one point as the origin, and then from there define the vector in another point's direction.
You want to say you could define vectors in other points' directions. Recognize that in a network, the positions of the points don't have any meaning, right? You're in a Facebook graph, right? He's in a Facebook graph. What is your Facebook position? Geometric position in Facebook. You don't have a geometric position in Facebook. Is that right? What? It's all topological. Facebook's just a data structure, and there's no geometric notion explicitly about it. But how can I turn a network like this into points? What would be a way to do that? What? So I'm saying you say maybe try to move the points around to respect the edge weights. Okay, make the edges vertices. Well, one idea, just to simplify this, would be, what if we took this adjacency matrix or this weight matrix and we computed an SVD, singular value decomposition of it? What did that do? Remember that approximated the matrix by a small number, by however many dimensions you wanted, right? So you could take the adjacency matrix or the weight matrix and do an SVD and pull off points in however many dimensions you want to represent the vertices. Is that kind of clear? How people see what I mean by that? Yes, okay? So in principle, what I want to say is we're going to talk a little bit, we're going to talk I'm guessing now, maybe at the end of the day, but if not, probably next class, we'll talk about clustering. Clustering is an example of a problem that can happen on graphs, or it can happen on points in space. Does everybody kind of see it? Well, clustering. I mean, if you have in Facebook, is there a natural cluster around you? Does it make sense to cluster the Facebook graph? Yeah, you say, okay, there's a cluster here, and this represents Indian graduate students, right? Okay? So it's clear that and again, that didn't assume that you were at points in space, you were just relationships, right? And a cluster was a dense region in the network, right? Does it make sense if I have a bunch of points, in space? Dot, 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 dot. Are there clusters? How many clusters are there? Okay? So it should be clear that there are certain problems that work naturally on both points and graphs, right? So the ability, so that's why I'm kind of mentioning graphs now. Because clustering, which is what I would do, obviously a thing you want to do on points is obviously a thing you would want to do on graphs also.
Sir,
Yeah.
One thing is like if Facebook represents all the nodes in 2D graphs, suppose.
Yeah.
So it's good, like we have lower dimensions, so we have better complexity. If we had suppose 10 dimensions, that would have been much more complex to every time find that cluster and something like that. Just because we have 2 dimensions, it is good, like we can just do
Okay.
quick.
So again, whenever you do a dimension reduction, the full network, Facebook network, is arguably 3 billion people by 3 billion people, right? If you compress it, is that better? Yes. Okay. You lose some detail, right? If you don't have the full adjacency matrix, are you really sure that you and I are friends? Okay? Mark Zuckerberg has the full matrix. He knows whether we're friends or not, right? If you compress it, yes, it takes up less space. Would you be able to tell for sure that there's a relationship between us? But the hope would be that, again, you would like to think that you could compress it enough so that it's much smaller and much better to work with without losing much detail. That's kind of what SVD was trying to do, right? You would like to have enough detail to capture the structure that you want, okay, but, have a much less unwieldy representation. Any questions? Okay, fair enough. So, given the time, again, when you talk about graphs, you should know that there's different kinds of graphs: directed, undirected, simple, not simple, and it's important to be able to talk about graphs, understand the vocabulary of graphs, so when you're talking to people, they know what you're talking about. But what I think I wanted to talk about, the one graph algorithm that I did want to talk about today was PageRank, okay? Because I know we talked about it a little bit back at when we talked in there about ranking scores and rankings, okay? And this is a famous, data science e-graph algorithm, okay? So what is PageRank? PageRank, you've probably heard of it from Google and stuff like this, is this idea that it sort of, given a graph, assigns a numerical weight to each vertex that is supposed to capture some kind of a notion of importance or centrality to that vertex to the network, right? You'd like to be able to take a graph and figure out which vertices are most important and which are least important. How in a graph, forget about PageRank, if I had to give some measure for in a graph in a network, what would be a measure of whether the vertex is important? Degree is a natural thing. You are more important than he is if you have more friends than he does in Facebook, right? That's what that would kind of argue, right? Now, PageRank is basically a generalization, refinement, or something like that tries to also factor in some sense, the quality of your friends, right? Right now, you may have 500 friends on Facebook. Donald Trump has 500 friends on Facebook, right? Those friends are right now better friends to have, or or Donald Trump, we can talk about that. But there's this kind of this notion here, right? Okay. So what is PageRank? PageRank is, mathematically, it's the idea that the PageRank of a vertex in a graph is sort of designed to be the probability that if you did a random walk on the network, you would end up on vertex V. Okay? That's kind of what we'd like. If a graph is more important, you're more likely to, vertex is more important, you're more likely to end there than otherwise, yeah.
But isn't that just a measure of degree? Where's the quality come?
Is that a measure of degree? It's not completely a measure of degree. Okay? I mean, you have to be a little bit careful here, because you could imagine a world where maybe you've got a vertex. There's several things you have to be careful about. Okay? You know, but one problem might be, let's say that you're a high degree vertex here versus a high degree vertex in a big crowd. Your degree is the same as my degree. Am I equally likely that if I walk around the network, I'm going to end up at both places? That's not obvious, okay? And you know, so it's a little, it's, you know, depends exactly what kind of, how you define random walk and various things like this.
Where does the notion of quality come from, though?
Okay, so what I would say, the way I would say, it's a question of, you're saying which is higher quality, this vertex or that vertex?
Well, because you said that it also factors in, like, how good the connections are.
Okay. What should be clear is that if you are connected to vertices that are high probability of being at, it's more likely a walk will come to you than a vertex if you're a vertex that has a low probability of being at. Suppose let's say you had somebody walking around the network, right? And there's popular places in the network and there's less popular places in the network, right?
Starting at those places, you'd imagine.
Yes, if I have 500 friends and they all live in the popular place in the network, then I am likely to get this thing. If I have 500 friends and they're all living in the ghetto, okay, then nobody's going to stumble across me, right? So that's the idea. But the truth is, there's a question of interpretation and what it is. PageRank is really computed by this formula. They say, what is PageRank? Well, darn it, this is PageRank. And what is PageRank? Okay, it is a function that says the PageRank of vertex V at time j. It's computed by an iterative algorithm. It's what it is the sum over all ingoing edges to vertex V of the PageRank of it at time j divided by, so it's going to be the sum of over all vertices V, U, which come into V. It's the PageRank of U divided by the out degree of U. Now let's think what that means. If U has a high PageRank, it gives V a high PageRank. Does everybody kind of see that? Now, if V has a lot of children, however, if U has a lot of children, it's going to be giving that high PageRank to a lot of other vertices. Does everybody see that? Okay. So, so what this is basically saying, my current PageRank for V is over all my neighbors I'm going to sum up. How powerful were they in the previous iteration, divided by how many vertices did they have to give their power to. Does everybody see this? And therefore, I'm going to get, there were votes at time j minus 1. When I do this again, I'm going to get now the votes at time j. I keep doing it long enough, the hope is that this should stabilize. Does everybody kind of see that? Any questions about what this computation is doing?
What is out?
Out is the out degree. This is out degree. It's supposed to be one word. Of U. U. So let's think about it. What is the power of me? What should the power of me be? I have got powerful friends, right? These friends have power. This is U. U has power. Okay, I will get power from you if there is an edge from you to me, right? But if this guy, if you think about it inheritance. How much of an inheritance am I going to be getting? Or my children going to be getting? Depends upon how powerful I am, and it depends upon how many of my kids survive to adulthood, right? Does everybody get, hopefully it's going to be 2, okay? And they will each get half my power. Does everybody see that? Donald Trump, I think, has 5 kids, right? He is big, he has a lot of stuff to inherit, but they're going to have to divide it by 5, right? Does everybody get that? And that's exactly what we've got, what our situation is here, right? The power I can get someone depends upon how much power they had and how many people they have to give it to.
Oh, it's just one word, out degree of.
Out degree is 1 word, right? Any question? Okay, if that bothers you deeply, send me email. I'll delete the dash from there. Any questions? Okay, fair enough. So any questions about how this computation works? It should be clear now that this is a relatively straightforward computation. Okay, that you start out with at time 0, you give everybody an initial power. What should be the power of every node at the beginning? Possibly everyone has power 1 over n, right? We give everybody equal power at the beginning, okay? And then we go through this procedure, and after every round, the powers are going to change. And when we get tired of doing it, that's what we say is the page rank. Any questions?
There is no means by which we can assign different powers to our children, like more to one, less to other. We cannot do that stuff.
So could we, okay, in this algorithm, in this variation of page rank, we assign all of our children, all of our the ones we have edges out to, we're giving them equal power. Yeah. If you wanted, you could imagine changing the algorithm where you give different people different powers based on, if you had a notion of how much you liked each of your children. Yeah. But that's not the classic page rank. Okay, any questions? Okay, so what is good about this? The basic philosophy is kind of that if you've heard the phrase, all roads lead to Rome, what is the conclusion if all roads lead to Rome? Rome has to be an important place, right? Okay? All roads don't lead to Stony Brook. Let's leave it at that, okay? So in general, it turns out that page rank is, this measure of centrality seems to be good at picking up important notions. So again, we used this on when we were ranking people in Wikipedia. We had all the pages of people in Wikipedia. And when you said who were the highest page ranked people in the Wikipedia graph, Napoleon was the highest page ranked person, right? He had famous people, a lot of people's articles linked to Napoleon, and a lot of people and places. He attacked a lot of countries in his day. They all linked to him, right? And they were powerful places. Why was Linnaeus? Who was Carl Linnaeus? Does everyone know who Carl Linnaeus was? Not the microscope. He was the taxonomy guy, the guy who developed the way people classify species. Why is Carl Linnaeus such a big guy in page rank? Every plant and animal links to him, that anything that he gave a name to, that linked to him, right? So, so that was a great thing for him, right? What? Why Bush? Because when I was doing this, Bush was essentially had been president for a long time, where every active leader in the world links their article, they had interactions with Bush. Bush was an important guy, right? When you delete the non-people ranks, Linnaeus went away. Does everybody kind of see that? And that's what you would kind of expect. So the lesson here is that PageRank does pick up notions of importance surprisingly well, and that it depends upon exactly what graph you give it. You give it a different graph, the PageRank is different, right? In this case, I deleted the non-people. You know, some people won by that, some people lost by that. Yeah.
Just out of curiosity, how do you differentiate between pages and people in this case?
How do you
differentiate between pages and people?
We had some kind of an we did. How do we identify which page was a person? I mean, the way we did it is people pages tended to have years that they were born and years when you died, right? And so